Welcome back to this afternoon session. So first we'll start with one talk on a specific topic, hardware development. Yeah, you can put it in full screen. So let me first introduce the speaker. So Dr. Hardik Shah got a Bachelor of Engineering in Electronics and Communication from India, then a Master of Science in System on Chip from Stockholm, Sweden. Hardik obtained his PhD from TU Munich on predictable and high-performance multi-core architectures. Currently, he is a regional sales manager at Lattice Semiconductor, and he has experience in developing with FPGA, teaching FPGA design, and selling FPGA. So the floor is yours.
Thank you very much. Can you hear me well? Okay, perfect. So first of all, I would really like to thank David, Francesco, and the organizers to arrange this special session for this topic. So really, thanks a lot. Okay, so before I begin, just a few words about the company which, of course, sponsors me and also sponsors this event. So I would like to bring your focus on mainly two numbers here. So by volume, Lattice is #1 supplier. So we supply maximum amount of FPGAs in the world, something like 250 million plus FPGA devices every year. And we are a tier 1 company, almost 40 years old. So if you are more familiar with Altera and Xilinx, so all these three companies, Altera, Xilinx, as well as Lattice, they were found from 6 months, 1 year, give or take, from each other. And we are a company based in San Jose, in California. And if you look here, then, oops, sorry. Oh. Okay, it needs a little bit of training. So our key market is industrial and automotive. Okay. And we are also active in communication, computing, as well as consumers. And you see many big companies are already using our FPGAs. There are some names listed here. So before we go into the topic, I would really like to encourage all of you to scan this QR code to register for Lattice Insights, which is our training platform. And registration is obviously free. But if you scan this code and register, tomorrow we are going to do kind of lucky draw from this audience. And the 3 winners will get Lattice evaluation board for free. So you have the board for free, and you have the training platform available. Many courses are also free on the training platform, and some courses are paid, but you pay like $99 or so. So please take this opportunity. If you cannot scan just now, please scan it later. The slides are already online. So just a few words about myself. Thanks a lot for introducing me already. As Matthew mentioned, I have PhD. I was also academic at one point, like 9, 10 years ago, and I'm feeling really happy. It feels to me like homecoming. Yeah, it's really great. And let's connect via LinkedIn. The rest is already said by Matthew. Okay, so now coming to the topic. At first, you may ask yourself, why low power, right? Few things are very clear. You have extended battery life, but on top, it simplifies your heatsink, right? It reduces complexity of power network on the PCB, and also it offers you to build or to use smaller packages because you don't have so much heat to radiate. So the footprint on the PCB of our components are small. Similarly, it increases component longevity because you have less thermal stress. And in some particular applications, you have heat-sensitive measurements. So because of low power dissipation from the device itself, your heat-sensitive errors are less. Okay, then the question is how? Okay, you are convinced now, maybe, I hope so, that low power makes sense. Then question is how? So it starts with company strategy. And if you read this in the yellow letters, that is mission of Lattice. We want to become, and we are, low power programmable leader. Okay? That is our mission statement that drives our company strategy with the right target market, and we have to select the right technology node as well as add right architecture features. We are going to briefly talk about all those points in the session, but I just want to give you a full overview that how Lattice came to this point. And of course, nothing is free in this world. So there is some cost to pay, okay? The cost is we don't use the latest technology node. We are not going into 2 nanometer, 3 nanometer, 5, 7 nanometer. So our latest devices, which are coming in the market right now, are 16 nanometer FinFET. Okay? So that is where we pay some cost. That's why we don't have the fastest fabric and fastest transceivers, let's say, and we don't have the largest FPGA device. But to many customers that we speak here, I cover, by the way, South Germany as well as Switzerland, and customers in this region say, hey, we are fine with what you provide already. We don't need, for example, 50 gig transceivers, 56 gig transceivers. We are fine with 15, 20, 25 gig transceivers. But since there is no option available in the market, we still have to pay for 56 gig transceivers, right? So that's where Lattice is actually in a sweet spot for those kind of applications, and we want to be there. This is our, let's say, mission from the company. Now, let me give a little bit of motivating example of building a low-power system. This is a little bit of personal story, okay? So when I was in class 8 or so, my life was simple. Because in an atom, there was only electron, proton, and neutron. But some people were not happy with my simplified life. So they built something like this. Maybe you know this. And in my simple world, this is still a big data acquisition system, right? So now we have, I don't know, bosons, we have quark, we have muons, something very, very complicated thing. But for me, the system is still very simple. This is data acquisition system with number of detectors, and then you have somewhere an aggregator, which is aggregating the data together and sending it to server or supercomputer, whatever you have here. Now, on the left side of this circuit, on the detector side, maybe from individual detector, the data is not so high. So you can live with low latency, but still not very high speed components. And as you move towards right side, the data increases, of course, data volume increases, and then you need high throughput systems. So Lattice targets actually these aggregator systems where you combine the data, you do some quick analysis, and send data for further analysis to server. Similarly, on the server side, there are some applications which actually does not require very high performance. They are board management controller or also PQC. So this is where also we have great solutions. That is post-quantum cryptography. And this is where flexibility is also required because the standards are not fixed yet. So FPGA is really in the right sweet spot of this. But going back to the aggregator, so aggregator can stay close to the detector, and their low power and small footprint are important. So this is where I'm just trying to give an example where Lattice FPGAs are used. Okay, now looking a little bit about products. So I spoke about that we are not targeting the fastest transceivers. We have, for example, our Avant family with Avant E, which is actually does not have transceivers. Then we have Avant G up to 12 gig, 12.5 gig transceivers, and Avant X up to 25 gigs transceivers. I'm not going into details of all the products because that is available in our website, and we can talk outside as well. We have a booth outside. You may say that, hey, okay, but I need something even less than 25 gig, but more than 12 gig. Then we have our Nexus 2 platform coming up, which is providing you transceivers of 16 gigs. By the way, both Avant and Nexus are 16 nanometer TSMC FinFET technology. So here is more on the graphical side. Also in terms of capacity, so here you see the capacity in terms of system logic cells, and here you see the transceiver speeds. If you want even less than 16 gig, below 12 gig, you can go to our Nexus platform, which has 8 gig transceivers. And Nexus was announced in 2019. Nexus 2 announced in 2024 in December, so announcement is rather new. And Avant was announced in 2022, which is rolling out now. Okay, so we are already kind of in the middle of the presentation. I hope that it makes sense and you are convinced that low power FPGA are useful. Now we are going to look into how we are achieving this. What are the architectural components we have employed in order to achieve low power consumption? So I think we know that low power has static and dynamic, two parts, right? We also know that especially when you have increase in temperature, your power consumption increases exponentially. Then power consumption also depends on capacitance of the circuit. So when you do the switching, you are actually charging and discharging the capacitance that is consuming your power. And then you have how many times you do the switching. So how many times per second you do it for million times or 100 million times. That's where all the charge and discharge cycle takes place, and that's where you consume the power. So basically, power is, again, voltage and a multiplication of voltage and current. And current then depends on these three parts. So you have static and bias part. By the way, most of times, these two are seen as only one, static. And then dynamic, which is depending on the switching or frequency, as we call. How many times do you switch the logic? And the bias here, D and A, they are all technology dependent. So that's why selection of right technology is very important. And as we spoke here, T, temperature, so exponentially proportional to power consumption is exponentially proportional to temperature. Okay, so now going into the key architectural enhancement that we have employed, we are going to talk about mainly three of them. So LUT4 and LUT6. Are you guys familiar with LUTs? Yeah, lookup table, right? That's a basic configuration cell or element of an FPGA. Then we are going to briefly talk about process node selection and other architecture features. Okay, so LUT4 versus LUT6. Lattice uses LUT4. And here are conceptual diagrams of LUT4 as well as LUT6. And LUT4 has 4 inputs. This means it has 16 configuration bits. And LUT6 has 6 inputs. This means that it has 64 bits of 64 possibilities on the memory side. Now, if you simply see from the diagram, you can clearly see that LUT6 is roughly 4 times size of LUT4. Yeah, 16 and 64. This means that you have clearly higher static power consumption. Then LUT4. LUT4, actually, as an individual element, if you look at LUT4, it is faster than LUT6. But when you are building complex circuit, sometimes LUT4 is too small, and then you have to cascade number of LUT4s in order to get your function implemented. That is where LUT6 becomes faster. So our competition, they are targeting LUT6. They are employing LUT6 architecture. We are employing LUT4 architecture. Okay? So you may ask, hey, why still LUT4? Why it is still somehow standard in industry? So it gives you actually good balance between complexity and efficiency. It has also routing simplicity and benefits on power consumption, as we discussed just now. Here are 2 articles you can check. We didn't sponsor these articles, by the way, so they are coming from really third party. And they were looking at number of designs to see how is the efficiency of LUT 6 versus LUT 4. So LUT 6, if you want to implement high-speed fabric, then it certainly makes sense. But you also end up having partially used LUT 6s because your design is not fully using it, and then your efficiency degrades. So I would really encourage you to go through these articles, very transparent, open. We didn't, again, we were not sponsor of this article. Okay, now going to the process node selection. So for our Nexus devices, for example, we chose FD-SOI technology from Samsung. And what you see here, this is bulk silicon process with such a big silicon channel. And compared to that, this is FD-SOI technology with such a small silicon channel. So this orange part that you see, I hope it is also there nicely visible. The orange part is the silicon channel. And then this, on FD-SOI technology, this silicon channel is sealed with ultra-thin buried oxide layer. The benefit of this in terms of low power is very clear, that you have at first less capacitance because your channel is so small. And there is always leakage current between channel and substrate. But because of this buried oxide layer, the leakage current is avoided. So we achieve extremely low power consumption because of this. But added advantage of this, and this may be interesting for some of your applications as well, is because of such a small area, there is less probability of a particle strike on this transistor. This gives us exceptionally well soft error rate. So we are way more soft error resilient compared to our competition who are employing bulk silicon process. And further advantage of this is you could actually create here, here bias voltage for to tune every transistor for either high performance or low power consumption. And that we provide here using software. So this is for our Nexus devices. If you has anybody used Nexus devices before? Okay. So maybe you know from the Radiant software that you could synthesize your design either for low power or high performance. And what actually happens in the background is you are tuning the voltage applied to this layer. And that changes the switching characteristics and gives you option to run even low power. Okay? And then there are some architecture features we will talk about. In Lattice, so all the components that you see here, PLL, RAM, ADC, etc., we can do frequency scaling, so faster, slower frequency, but we also completely disconnect the power supply, voltage supply to it. So that is how you do a voltage scaling and you save power again. So this is again architecture decision that we made. In our power estimator, you have also possibility to mention for every module the efficiency factor or effectivity factor, sorry, that determines for how many time this component will be turned on and for how many times it will be turned on. So you get also, this entire process is incorporated in our power estimation as well. Okay, and this is again one of the architecture feature that we employ to reduce our power consumption is all our Nexus devices as well as small XO devices, they have extremely fast boot up time. So XO devices starts in 1 millisecond, and you see here the Nexus devices in 830 milliseconds. And many of our customers, what they do is when they have task which has periodic activation time, then in between, they just turn off the FPGA. This saves significant amount of power consumption. Okay. So then I'm at my last slide, actually. Again, just kind of summary. Low power is the key focus of Lattice, as I mentioned earlier. That is our mission statement, driven completely from strategy to process node selection, architecture, and enhancement everywhere. And OK, so just listed some strategies or some tactics that we employ in order to achieve low power. And again, I would like to encourage every one of you to scan the code and register for Lattice Insights in order to win the lucky draw tomorrow. Yeah, thank you.
Thank you, Hardik, for this comprehensive presentation. Any question? Sorry.
Hello. Thank you for the talk. Very interesting. I was wondering, especially for the tools to program your FPGAs, what is the support for Linux or other OSs except from Windows? Because last time I used it was very good on Windows, but it's quite tricky to get it working on Linux.
On Linux?
Yeah.
I think we have solution on Linux as well. Windows is maximum our customer base they are using. Yeah.
Is it just Diamond, or you have more software for your programming?
We have two softwares,
yes.
So Radiant and Diamond. Mm-hmm. So Diamond is mainly for our control FPGAs, Mark XO3, Mark XO2, if you have used. They are a bit small FPGAs. And then for our Nexus and Avant and Nexus 2 devices, we have Radiant software. So Radiant is our new software which receives 4 updates per year.
Okay.
2 major updates and 2 minor updates.
Any other question?
I have another question.
Please, Davide.
So you spoke a lot of low power, which is one of, let's say, the requirements here at CERN, especially for front-end application, where it's important that we don't heat up too much our circuits. Another requirements typically here at CERN is radiation hardness, especially in some environment. So I was wondering if any of your FPGA has been verified for high radiation hardware environments. Thank you.
Yeah, thanks. This is a very good question. So at first, we differentiate between radiation hardened and radiation tolerant, right? There are 2 differences. So we employ special screening in order to make the devices radiation tolerant. And also because of Nexus, as I mentioned, because of small channel length, this is inherently good for radiation effect. But if you are interested, we can talk outside, and we can bring the solution which is more radiation tolerant.
Yeah, please.
Just a quick question. Like you might already say, is it like SRAM based or flash based FPGAs?
Which base?
SRAM or like static RAM or the flash?
So they are. We have all these devices are volatile devices. In our XOR devices, we have flash integrated. So you can at boot up, the configuration can be loaded from flash to the FPGA. But they are SRAM based. Yeah, to give you an answer.
Thank you.
Hello. I just would like to ask you about the software tools again. If you can tell us what is the roadmap, specifically talking about Edge. So you just tell us that there are different the tools, so there is Lattice, but then you offer different software tools for different FPGAs. Is there any integration idea or what is the reason to have different softwares there?
Why we have 2 different tools?
Yes.
Yeah, so main reasons for having these 2 different tools are legacy reasons. So we, in 2019 or so, when we came up with Nexus technology, we kind of changed too much. It was like a completely revolution of our devices. And then we started also with the new tools. But we realized that many of our customers, so we provide or we keep providing the devices in the market for 20 plus years. And many of our customers, they have been using our devices in also qualified environment, so they cannot change the tool. So we kept that branch alive and kept all our new devices towards Radiant.
But should we expect that in 10 years, then will be the same case, that we'll have different software tool for a different
No.
offering?
Right now, there is no plan like that. We have only two tools, let's say. One is Diamond tool, which is old, right, and which will be supported also for the old devices. And the Radiant tool, all our new devices will move to Radiant tool. So we are not planning something like a Radiant 2 in future. No, nothing like that.
Thank you.
No more question? Okay, so let's thank the speaker again.